Hi, today we have a question which is a balloon is being inflated with the water supply of 0.6 meter cubic per second as shown there. Find the rate of growth of the radius at the instance when the radius is equal to 0.5 meter. So here the question given, here is the balloon and here we have the velocity inlet, and actually here we have the outlet. Let's say this is velocity coming to the balloon and it will expand the velocity outlet V velocity to expand the balloon, so it will be surrounding, it will in this direction. The velocity will be outward from this balloon. Alright, so let's say that this is velocity R. So we need to draw the control volume. Alright, so the first we need to analyze what the question asks. Find the rate of growth at the instant when the R equal to 0.5. So from here, the rates of growth we need to find the rates of growth of radius. So dr, right, over dt. This is definition of rate of growth for the radius. So the question we need to find is dr over dt. Since we know that the velocity is moving outwards with the direction of r, so here is actually velocity r, radius. So the question asks what is the velocity of Vr only. Alright, indirectly they said that the rate of growth of radius. So dr over dt is actually equal to v, velocity at direction of r. So applying our Reynolds transport theorem, alright, step number 1. Apply the Reynolds transport theorem where we need to convert from the system to the control volume. We got here is d over dt n of the system, right, and then equal to d over dt integration of control volume intensive property multiply with rho dv plus the integration of control surface intensive property rho v dot n product unit vector dA. Right? So from here we do assumption that the total flow of the system is steady. Alright, assumption number 1 is the total flow of the system is steady. D over dt of the system is equal to 0. It is steady flow. And then there is no change of we call here, alright, water. There is no change, the rise or drop of water. So it is constant, alright, across the control volume. So we can say that the assumption number 2, d over dt, right, the control volume intensive property rho dv is equal to 0. Also steady inside the control volume. Thus, step number 2 is we need to simplify the RTT We cancel this one equal to 0. We cancel this one equal to 0. And remember that this is the water. And then another assumption is density is constant. Alright. Density inlet and outlet is constant. Alright. So, step number 2, applying the Reynolds transport theorem, only leave only this term, which is 0 here. This is 0 equal to integration of control surface intensive property rho v dot n dA. And then we have how many points? Consider this is point number 1. And then this is point number 2, outlet, right? So point number 1, control surface, 0 equal to intensive property we need to define, alright? Since the intensive property we can consider as the mass, alright, the mass of water. Alright, when it is involved of water, water or air, we can consider as the mass. So here, in order to get the intensive property, extensive property divided with mass. So the mass, the extensive property is the mass. So mass divided with mass is equal to 1. So the intensive property is 1. We replace here with 1, and what we got here is basically 1 multiplied with density rho v. This is rho 1, velocity 1. Alright, this is you can say that point 1 is into the control volume. It is negative here, dA, which is we can replace with area because it is uniform velocity. And point number 2 is out of control volume, which is plus rho 2 v2 a2. This is a1. So rearrange the equation, move to the other side. Rho 1 v1 a1 equal to rho 2 a2 rho 2 v2 a2. And since the density is constant, we can cancel out density, only leave v1 a1 equal to v2 a2. So actually v2 is actually velocity of radius, of direction, of radial direction. So we can actually replace v2 with pr. Okay, so rearrange step number 3, rearrange the equation, leave it pr to be the subject. So v a1 over a2 multiply with v1. Okay. So area 1 supply. Okay. It is given that the water supply, this is given. The water supply, this is volume flow rate at Q1. Alright. So this is volume flow rate at Q1. Thus, we can use the equation. We can replace this one, basically, this term with Q1. So we rearrange the equation. Alright, VR become the subject, Q1 over area 2. So the question is how to get the area of the sphere. So remember that we have the area of the sphere is, the formula is, right? Remember the area of the sphere is equal to pi 4 pi r squared. Alright, this is the area of the sphere. Because we consider this one as the area of the sphere. So just substitute the equation. Q1 given here is 0.6 over area of the sphere. 4 pi radius is here 0.5. It is given at the instant of 0.5. So just substitute here 0.5 squared. Thus the final answer is 0.191 meter per second. This is basically the same with dr over dt. Thus the final answer is 0.191 meter per second.